All right, Chapter 7, Section 7.1, trig identities. What's an identity? What's an identity in general?
It's who I am.
It's who I am? Okay. What's a mathematical identity?
Who the numbers are.
No, it doesn't have anything to do with the word identify. An identity is an equation that is always true. For example, 2 times x plus 5 equals 2x plus 10. That's an identity. Is that true for any number x in the whole wide world that you plug in? Yes, so that's called an identity. It's an equation which is always true no matter what number you plug in for x. All right, so that would be called an algebraic identity. We're going to look at trig identities. We already know a whole bunch of trig identities. Anybody give me one? Cosine is not an identity. That's not an equation. Can you get? There's an identity. All right, so identities we know. Here's a list. I don't need to number them, I guess. Tangent of x is sine x over cosine x. There's an identity. And we have another one about cotangent. Cotangent x is cosine x over sine x. So there's a couple identities we know. What other identities do we know? Cosecant is 1 over sine. Cosecant x is 1 over sine x. This one could also be written, I could flip both sides, and I could also write this one as sine x is 1 over cosecant x. That one could be written that way. Very similarly, secant x is 1 over cosine x, or cosine x is 1 over secant. One. How about this one? Tangent x is 1 over cotangent x. Is that true? Yes, because tangent and cotangent are just reciprocals of each other. All right, so this one could also be written as cotangent x equals over tangent x. All right, so these last 6 that I've written, these are known as the reciprocal identities. Why are they called reciprocals? Because they're flipped. 1 over sine is cosecant. That's a reciprocal. 1 over something is known as a reciprocal. All right, so there's a bunch that we know. Any others? No? Maybe? Probably? All right, there are some others we've talked about, but we haven't used them a whole lot. All right, so what if I were to draw this triangle right here? This is my angle x, this is A, this is B, and this is
sine is
That's not really what I'm looking for. This is a right triangle. What's the famous formula you know about right triangles? That's the Pythagorean theorem, right? A squared plus b squared equals c squared. All right. What can you tell me about sine of x in this triangle? So it would be b over c, wouldn't it? So sine x is b over c, and cosine x would be a over c. So sine squared x plus cosine squared x, not tangent squared. It turns out to be 1 because this would be b squared over c squared plus a squared over c squared. I have common denominators, so I can go ahead and add these together. What's b squared plus a squared? b squared plus a squared is c squared. That's the Pythagorean identity, Pythagorean theorem. So this is c squared over c squared, which is a fancy way of saying 1. All right, so we talked about this identity back a while ago, way back in chapter 1 when we did when we talked about sine and cosine in terms of writing, in terms of the unit circle. It also turns out it works for triangles. And this is known as the Pythagorean identity. Because it comes directly from the Pythagorean theorem. Sine squared x plus cosine squared x equals 1. What if I were to take this nice identity and I divided everything by cosine squared? I would be left with tangent squared x. Sine divided by cosine is tangent, so sine squared over cosine squared is tangent squared, plus 1 equals secant squared x. I could also take this same original identity and divide everything by sine squared. And if I divided everything by sine squared, I would have 1 plus cotangent squared x is cosecant squared x. So those are all called the Pythagorean identity, even though there's 3 of them. They really ought to be called the Pythagorean identities, but they're usually not. It's usually considered a singular entity. Questions about that? All right, the last, there's 2 more identities that we should know. 2 more groups. Even odd. Remember what the graph of sine looks like? The graph of sine looks like this, like so, on the other side too. Cosine is shifted. Is that an even function or an odd function? A 50-50 chance of being right?
Even.
And you're wrong. It's odd. The rule for being an odd function is, if I turn it upside down, I have the same picture. That's the rule for an odd function. Odd functions are symmetric with respect to the origin. All right, so the algebraic rule about odd functions is that sine of negative x, when you have a negative in there, for odd functions, the negatives come out front. We did this. You're right, we did this. Again, we did it back in chapter 1, I think. And, I mean, here's the deal. We kind of know this. What if, like, x is negative 45 degrees? What's the sine of negative 45 degrees? Well, where's negative 45 degrees? In quadrant 4, and in quadrant 4, sine is negative. All right. Now, what can you tell me about the cosine graph? It's shifted and it's even. Why is it even? Because it's not the same when you flip it over. That's true. What is it the same as? That's not very good. Well, what I really meant was, if I could cut this right here and fold it over, it's symmetric with respect to the y-axis. Correct. And that means it's an even function. And the rule for even functions is cosine of negative x. What does cosine do to negative things? Like, what's the cosine of negative 45 degrees? Negative 45 is in which quadrant? And cosine is positive in quadrant 4, isn't it? So it makes everything positive. So cosine eliminates negative signs. If you have a negative sign in here, cosine just destroys it. When you're dealing with sine, when you have a negative in here, the negative comes out front. Tangent is also an odd function. So for tangent, negative signs come out front. And same deal. If I give you a negative angle, something down in quadrant 4, tangent is negative down in quadrant 4. So the negative sign just...
So those are all identities.
Those are all identities. That's correct. Those 3 more identities. The last ones I don't think we've talked about. Cosine of x is the same as sine of pi over 2 minus x. What's that all about? Well, there's 2 ways to think about it.
Oh, wait. Can we think about it the way that we used to do the graphics?
That was the first way. That's why I pulled the graphs back up. Here's my sine graph. Here's my cosine graph. How are they different?
Well, they're shifted.
They're shifted. How much is the shift?
Pi.
It's pi over 2. So there's a shift of pi over 2. If I take this cosine graph and I move it over this way, pi over 2, this would come right here and it would look just like a sine graph. Okay? So sine graphs and cosine graphs are the same, they're just a shift of each other.
Would it be x minus
Well, it turns out that because sine is odd and it destroys negative signs come out front, you get the same thing. It's usually written this way, but you're right, it would be the same as sine of x minus pi over 2. But you're right.
I'm saying, with the shift change, that is for the period. That's not for the period. Shift.
If it was multiplied, that would be the period.
Oh, okay.
It's not added. The reason it's usually written this way is because of triangles. I'm going to draw you a triangle here. If this is angle x, and this is opposite, this is adjacent, and this is hypotenuse, then what's the cosine of x? Adjacent over hypotenuse. If this is angle x, what's this angle up here? Y, that's true. Not the answer I wanted. How big is this angle?
180 minus 90 minus x.
180 minus 90 minus x. So that's 180 minus 90 minus x, which is the same as 90 minus x, which is the same as pi over 2 minus x. So that's why this formula is usually written this way. This angle is pi over 2 over x. The sine would now be this side over that side. So the sine would give you the same answer as the cosine. All right? And these all work for all the other functions too. I can do sine of x is cosine of pi over 2 minus x. Tangent of x is cotangent of pi over 2 minus x, so on and so forth. I'm not going to write them all down. Secant x is cosecant of pi over 2 minus x. And I can switch the tangent and the cotangent here. I can switch the secant and the cosecant here, and those all work. And it's really all because of this triangle. What's that? That's all of them that we know for now. We'll have probably about 40 or 50 more identities in this chapter before we're done. This chapter has lots and lots of identities in it. You will not have to memorize them all. No, you will not have to memorize them all. I will give you some of them for the exam. No.
Why would we need one?
I'll tell you what you need to memorize, and then I'll give you the rest of them. So I'll tell you right now that you need to memorize these. which I think you already know. So you need to memorize those. I will not give you those on a test. Those you should know. You will also need to memorize the Pythagorean identities. Those you will need to memorize. If you know one, you really know them all. Because once you know one, you can figure out the others by just dividing.
Yeah.
Correct. So if you know one, you really know them all. That's right. And that's probably about it. Probably all the rest of the identities that you're going to need to know, I'm going to give you a formula sheet for the test, and they'll be on there. Okay? If there are any others that you need to memorize as we go, that I want you to memorize, I will tell you need to memorize those. But otherwise, you can assume you don't need to memorize. All right, so here's what we're going to do in this section. We're going to use all those identities that we just had to do two things. First off, we will simplify expressions. And then later, we will verify identities. All right, so we're asked to simplify this expression. Any good ideas on what you might do? The tops cancel out to be 1. Why do the tops cancel out to be 1? All right, so one of the things we typically do is we convert everything to sines and cosines. Oops, that's a cosine x. I think I'll leave this one alone for now, cotangent x. But you're right, so right on the top there, those two things reduce. So I'm left with 1 over cotangent x, t, the problem used t in the beginning, I should use t's.
No, top is x, cotangent is t.
That's supposed to be an x. All supposed to be the same letter there. Teacher screwed up when he typed it up. All the same letter. Anyway, what would you do with 1 over cotangent of whatever that letter is supposed to be? It equals tangent of supposed to be x. I think that's the answer they're looking for there. Simplify a little bit. All right. How about B? Any clever ideas? All right, that's one of our techniques is to switch everything to sines and cosines. So I would do that. That's 1 plus 1 over sine y. Okay, that's a good idea. Although it doesn't look more simple, it looks more complicated so far. So I don't think that's the final answer. Any ideas of what to do next? Next. That first step was a good first step. The ones can't cancel because these things are connected by plus. This sort of thing is known as a complex fraction, where you have a fraction and then another fraction. What do you do with complex fractions? You can't just flip it, unfortunately, because it's connected by the plus. Close, not 1 over sine. Multiply just by sine. So you look at your complex fraction parts. This is the only one, and you find the common denominator. Well, there's only one denominator. It's sine. So what I'm going to do is I'm going to multiply the top and bottom by sine. And I especially want to do that on bottom. I'm going to take this sine, and of course I've got to distribute it through. What's sine y times 1? Sine y, that was a trick question. Plus, what's sine y times 1 over sine y? 1. So you see how that gets rid of the complex part of the fraction? Gets rid of the fraction within the fraction? All right, up on top, I don't think I'm going to multiply. I'm just going to leave it 1 plus sine y times sine y. And then I think a good thing happens. What's the good thing that happens? The 1 plus sines reduce. 1 plus sine and sine plus 1 are the same. And final answer? Sine y. All right. So so far we've learned two techniques. Technique number one, we convert things to sines and cosines. Technique number two, when we have complex fractions, we multiply to eliminate the complex fraction thing. Very common techniques. How about C? I might. That's not a bad idea. That's one of the things we do quite often, is we convert things to sines and cosines. But I see something different here. What I see in this problem, whenever I see something being squared, I see the Pythagorean identities. So what I'm looking at, up on top, that tangent squared, how could I rewrite tangent squared? Secant squared minus 1. So tangent squared is secant squared minus 1. So that's the third common technique that we look for. We look for sine squareds and cosine squareds. That's an indication of Pythagorean identity. Tangent squareds and secant squareds, Pythagorean identity. All right, so I'm going to take this and rewrite it. This is 2 plus, instead of tangent squared, it's secant squared minus 1. Secant squared x over secant squared x, and then we still have that minus 1. All right, does that help at all? I can combine my like terms up there. Okay. So that's 1 plus secant squared x over secant squared x minus 1.
Can we do the 1 as 1 over 1 and multiply? Well, 1 would be 1 over 1, and then we would multiply, so it would be secant squared x over secant squared.
Okay, what Brandon is saying is a wonderful idea. He says, I have a fraction here and a regular old number there. I want to add them together. Well, subtract them, actually. I said add. He said subtract. To subtract them, I have to get a common denominator. The common denominator is secant squared x. So I multiply top and bottom of that one by secant squared x. Then look what I have. I've got secant squared x on bottom.
Half is 1.
What do I have on top? Just the number 1. Because a secant squared minus secant squared, those add up to 0, don't they? All right, so final answer, what's 1 divided by secant squared? Cosine squared. So I think that's what we want for our final answer there is cosine squared. A little complicated. That one was a little complicated. Questions on that one? Yes, but not in this section. They'll get harder as we go, I promise. That's probably about the hardest one in this section. All right, so that was 1, simplify the expressions. 2, verify identities. In a sense, verifying identities is easier because it's really the same thing, except they're telling us what the answer should be. So we start with the left-hand side. What they're saying is you should be able to simplify the left-hand side, and your answer when you get all done should be sine x. So it's kind of like this is an identity we just verified. 1 plus sine y over 1 plus cosecant y is sine y. So now I'm telling you the answer better be sine y. Show me that you can make it work. All right, so we're going to start with the left-hand side. Tangent x over secant x. And you're going to convince me that you can do some stuff and simplify, and your answer should just be sine x. What kind of stuff are you going to do?
The easiest way would just be, it would be sine over cosecant, and then 1 over, sine over cosine, and then 1 over cosine.
All right, so again, there's one of our very common techniques. One of our very common techniques is to switch everything to sines and cosines. So that's a good idea to try. How do I divide two fractions? Flip and multiply. So that's sine x over cosine x times cosine x over 1. Now I'm very happy. Those reduce. And we are left with sine x like they told us we were supposed to be left with. Questions on that one? All right. How about b? Sine x plus cosine x squared. What can you do with that? Distribute. Okay. So you're saying write it as sine x plus cosine x times sine x plus cosine x, and then distribute it out and get what you get? Yeah? Okay. When I do that, sine times sine, that's sine squared. So I have sine squared x plus outside gives me sine x cosine x plus inside gives me cosine x sine x, and finally the last give me cosine squared x. So far it looks like we made it worse. Can we make it better?
Well, it would be 2 sine x.
So the 2 in the middle, that's 2 sine x cosine x. I just wrote it weird. And what about the 2 on the end? When you add them, it's 1. Why? That's the Pythagorean identity. So again, right away when I saw this problem, I saw a square. So immediately I was thinking I'm going to use the Pythagorean identity somewhere. And that's where it comes up. Sine squared plus cosine squared is 1. And then these 2 in the middle, I can change the order here. This is really sine x cosine x. So there's 2 of those. 2 sine x cosine x. And I got the answer that they wanted me to get. Let's try C. Tangent theta plus cotangent theta. Sine over cosine plus cosine over sine. All right, so again, very common thing. We started by converting everything to sines and cosines. Now what? You have 2 fractions. How do we add 2 fractions? We get a no, we don't flip that.
Oh, no.
To add 2 fractions, we get a common denominator. What's our common denominator? Yeah, this one has a cosine, this one has a sine. So my common denominator is going to be cosine theta sine theta. Okay. First fraction, what did I have to multiply the bottom by? I had to multiply the bottom by sine, so I had to multiply the top by sine. So sine squared. Yeah, sine squared theta. Second fraction, what did I have to multiply the bottom by? So I better multiply the top by cosine. That gives me cosine squared theta. And then I'm seeing something I really like. What am I seeing? Sine squared plus cosine squared is 1. So this is 1 over cosine theta sine theta. Having the cosine on bottom, that's a secant. And having the sine on bottom, that's a cosecant. And I got exactly the answer they told me I should. Questions on that one? What's that? It is a lot of memory stuff, I agree. But it's a lot of patterns. I mean, almost every problem we've done the same way. We've converted to sines and cosines. We do that a lot. We've gotten common denominators. You do that a lot. You use the Pythagorean identity. I mean, those 3 things show up in almost every problem. like little puzzles. D. What do you see on D?
Oh, what's it called? Does it start with a C?
D starts with a C, yes.
Oh, you know when it's the same thing except instead of addition, it's subtraction?
Yeah, that begins with a C.
It's the, I know. I can't remember the name.
Anybody
What's
remember?
the second one?
What's that?
Conjugate.
Conjugate. Complex conjugate would be when I have complex numbers here. But if one's a plus and one's a minus and they're otherwise exactly the same, they're called conjugates. Complex conjugates would be when you have complex numbers. Very good, conjugates. So what do we do? We're looking at fractions. We're adding stuff together. When we're adding fractions, we have to get a common denominator. Correct. So the fact that these are conjugates is nice. Truly not really that important. Although you worked very hard to come up with that word. That's good. But the important thing is we have two fractions. When we have two fractions, we need a common denominator. The common denominator is multiply those two things together. That's right. That's always a common denominator. So our common denominator, we're going to have secant x plus tangent x, and then secant x minus tangent x. In a minute, we're going to FOIL it out. Yes, darn right we are. And it's nice that they're conjugates. Why is it nice that they're conjugates when we FOIL them out? Because we know the middle two pieces will go away. All right. All right, so up on top, what do I need on top of the first fraction? No, I got to get common denominators before I can add. So the first fraction, I multiplied the bottom by secant minus tangent. So I better put a secant minus tangent up on top. And the second fraction, I multiplied the bottom by secant plus tangent. Well, let's add the tops, because we can add the tops. I like it when I add the tops. What do I get when I add the tops? 2 secant x. That's supposed to be my final answer, 2 secant x. But we got to keep going, don't we? We got to FOIL the bottom. When we FOIL the bottom, we get secant squared x. The middle two terms cancel out because they're conjugates. Minus tangent squared x. I now see secant squareds and tangent squared. So what am I thinking? I'm thinking Pythagorean identity. Anytime I see squares, I'm thinking Pythagorean identity. So if I take secant squared minus tangent squared, what do I get?
Well, tangent squared x plus 1 is
So what's secant squared minus tangent squared? Positive one, because I would move this tangent over here. Secant squared minus tangent squared, I would move the tangent squared over there. Secant squared minus tangent squared is 1. So the whole denominator, that's a fancy way of saying the number 1. So I get 2 secant x, just like I was supposed to. Yeah, the verifying ones in a way are easier because you know what the answer should be when you get all done.
You got 5 minutes.
I got what? 5 minutes? I got 6 minutes. I go by that clock. We started by that clock, we end by that clock. All right. This one, has something a little new in it. I can't convert the sines and cosines, can I? There are already sines and cosines, so we can't do that.
Can we unconvert
I suppose we could unconvert them, but I don't know what we would want to convert them to. I can't cross multiply. I can't cross multiply this way and that way.
Because that's the answer.
Because that's the answer. The only time you can do that is when you already know it's true. So when you're dealing with identities, you have to start with one side, do a bunch of stuff, and get to the other side. You can't use both sides at the same time. That's cheating. Not cheating, but illegal. All right. So this one has something a little different, something we haven't seen yet. But this is a very common thing. If you see a 1 minus cosine, or if you see a 1 plus cosine, or a 1 minus sign, or a 1 plus cosine, any of those four things, you should be thinking conjugate. So I see a 1 minus cosine, I'm going to think conjugate, and I'm going to multiply it by a 1 plus cosine.
Oh, you did this.
Yeah, you did this multiplying by conjugates you probably use to rationalize things. Same sort of idea. So, again, same trick though. If you see a 1 minus cosine or a 1 plus cosine, or they have signs in them, you should think conjugates. And here's why. What happens up on top when I FOIL those out? Again, they're conjugates. So the middle terms go away, and what am I left with? 1 minus cosine squared x. Why is that important? What do I see now?
Because if you where'd you get that?
I multiplied the tops out. 1 times 1 is 1. Because they're conjugates, the middle two terms go away. Cosine squared. What I see now is I see a cosine squared. What do I think of when I see a cosine squared? I think of the Pythagorean identity. No, just look at this first one. Right, if I move the cosine squared to the other side, I would have 1 minus cosine squared. 1 minus cosine squared would be the same as sine squared. So my top, that's why we use conjugates. We use conjugates a lot to force the Pythagorean identity to show up. We're not done yet. Down on bottom, I'm just going to leave it alone. I'm going to leave it as sine x times 1 plus cosine x. Sine x times 1 plus cosine x. And then a fairly nice thing happens. What's the fairly nice thing? I can reduce. I can reduce one of the signs on top with one of the signs on bottom. And what am I left with? The answer we were supposed to get. Alright, so again, when you see something like this,
Can you go over the 1 minus cosine?
yep. Normally, we write the Pythagorean identity as sine squared x plus cosine squared x equals 1. But I could take this and subtract cosine squared x on both sides. And then I would have sine squared x is 1 minus cosine squared x. And you can do the same thing, and you can write cosine squared x as 1 minus sine squared x. So those are alternative forms of the Pythagorean identity that you should start to recognize. Okay? These last two problems, we'll do those on Monday when we come back, and then we'll move ahead into chapter 2. Section 2, I mean.